What's up, guys? Welcome back to a brand new YouTube video. Today we're going to be talking about limits and derivatives, and we got like a syllabus or whatever we're going to cover here. All right, so first let's talk about what a limit is and the limit notation, how we write a limit. First, let's choose any function. All right, we're just going to choose x because that's pretty simple. Then the limit is saying, so let's say we write limit x tends to 0. So what are we saying? Basically, we're saying evaluate this function as x gets closer and closer to 0. If you guys know what an asymptote is, where you have like a line and then a function is getting infinitely closer to that line, but it's never touching, that's basically what we're doing with x. All right, we're saying we're going to get closer and closer to 0. The value of x is going to get closer and closer to 0, but it's never actually going to equal 0. And then we have to find the value of x at that point. So our first method to evaluate the limit is going to be direct substitution. If we don't break any laws of mathematics, then we can just directly substitute this value that we have for the limit in for x. And when we substitute that in for x, we get that this equals 0. All right. So now we have a basic understanding of what a limit is. We're just saying x is getting closer and closer to that point, but it's not going to be equal to exactly that point. Now you might see something like this. Limit x tends to 0 from the negative side. All right. So to evaluate this one, to let you know what this one looks like, or to show you what this means, it basically just means we're approaching x from this side. All right. So say we have a function which goes across like this, and it's like a piecewise function. So uh, it comes here, and suddenly it teleports up here like this, right? If we approach x from the, if we, and this is 0, of course, the origin. If we approach x from this side, coming this way, then we see it's equal to, I don't know, let's say that this is equal to like 1, and then this is equal to like, it looks like about 4, right? So if we approach it from the left side, because of this negative sign, we can see it equals 1. So this limit would evaluate to 1. Meanwhile, if we instead did x tends to 0 from the positive side, that means we're coming in from this direction. We can see that this is going to be equal to 4. All right, makes sense. Now, what if instead we did this exact same thing where we have this same, hold up. What if we did this exact same thing where we have the same kind of like weird function, a weird piecewise function, but instead of saying plus or negative sign, we just said limit x tends to 0. What would this value be equal to? Well, if we don't have like a negative sign or a plus sign here, if there's nothing here at all, then the limit has to be the same from both sides. Okay, otherwise it just doesn't exist. It's undefined. So this is going to be undefined. What if we had something like, what if we had something like this, where it's going to infinity this way? Well, then we can see from both sides, it's approaching infinity. So this would be equal to, so this, the limit x tends to 0 here would be infinity. Or let me clear that up a little. Let me clear this up. Okay, so here we can see that this function, from both sides, it's going up to infinity. So the limit of x tends to 0 would be equal to infinity, basically. What if instead this is going to be the function 1 over x, which looks something like this, something like that, and then like that. What would the limit x tends to 0 of this function be? Take a second to think about it. Basically, we can see that this is going to positive infinity, this is going to negative infinity. They're not equal to the same value. Both the limits aren't equal to the same value. So basically, what we're doing here is we're seeing if the limit from the positive side equals the limit from the negative side. And if those two are equal, then we can basically just say that, the actual limit with no positive or negative sign is equal to whatever that value is. But we can see this is going to negative infinity and this is going to positive infinity, so this is going to be undefined as well. Let's do one more interesting thing with limits. Let's say we have limit x tends to infinity. Okay, so you can already see where this is going to be defined and where this is going to be undefined and where. So if we have something like, e to the power of x, which looks like this, we can see as x goes to infinity, y is just going all the way up to infinity. So the value of this is just going to be like infinity, right? On the other hand, if we have something like, let's go back to that 1 over x example, 1 over x like this, then we can see as we go to infinity this way, x is getting closer and closer to 0. Whoops. So limit x tends to infinity of 1 over x is just going to be equal to 0. Uh, just like that. Okay, so now we've covered endpoint behavior. Let's look at let's look at direct substitution actually. Okay, so we already talked about how direct substitution works for um so let's look at something like this. Let's look at x tends to 0 for 1 over x. We can see here that basically 0, when we plug this in, we get 1 over 0. And 1 over 0 is undefined, right? 1 over 0 is undefined. So the answer is just going to be undefined. When we have something like this, you can just say that it's and we plug it in directly, we get an undefined answer. So we see the answer is undefined. Um, another thing we could do is say we had something like this, right? We got limit x tends to negative 1, x plus 1 divided by 2x squared plus 3x plus 1. Um, we're going to talk about the factor and cancel strategy here. All right. So first, let's follow the first step, right? Factor it out. This one is already completely factored out, but we can factor this bottom one out. We have 2 and 1, so we have to get some two numbers that when added together equal 3, but when multiplied together equal 2. Um, so that's just going to be 2 and 1. So we have 2x squared plus 2x plus 1. Sorry, plus 2x plus 1x plus 1. So this equals 2x times uh, x plus 1. And then we just have plus x plus 1. And we got 2x plus 1 times x plus 1. Okay, and on the top, we have x plus 1. And wow, look at that. X plus 1 cancels out. And we're left with 1 over 2x plus 1. Now we notice when we directly try to substitute this, let's directly try to substitute this, right? We have x plus 1 on top, okay? And we're plugging in negative 1. So we have negative 1 plus 1 divided by 2x squared. X squared is 1. So that's 2 minus 3 plus 1. And we get 0 divided by 0. This is really special. This is called indeterminate form. Okay? You might be inclined to say that we have a 0 on the bottom, so this is just undefined, and we can use the exact same strategy as before and just say that this is undefined. But that's not true. When we have indeterminate form, when it's 0 divided by 0, that means we still have more work to do. There's a way we can find an answer, right? And usually this is going to happen when you have a function like this, right? Where you got like your function, but there's going to be a hole right at your limit. There's a hole right on your limit. So when you try to evaluate it at that point through direct substitution, there's a hole. It doesn't exist. But the limit from both sides exists. So there's still one value that it converges to. And now that's the value we're trying to find here. And when you have something like that, you're going to get this indeterminate form. All right, but we can still find that value, right? You'll notice what we just did here is after factoring it out, we cancel out the x plus 1, and this x plus 1 term here that was on the bottom, this is the one that's causing our function to be undefined, right? Because we're trying to find the value where x equals negative 1, and then my negative 1 plus 1 is going to be equal to 0, making the entire bottom 0. And this is basically what's messing us up, right? But when we cancel it out with the top, that goes away. And now we're left with 1 over 2x plus 1. And now we can use that direct substitution. 1 over 2 times negative 1, that's just going to be equal to negative 2 plus 1 equals negative 1. Make sense? I hope that made sense. All right, so now let's talk about the rationalized strategy, which is best explained through an example. So let's look at this thing where we're finding the limit where x tends to negative 5. Tends to negative 5. So first off, straight off the bat, we can see we have a 5 on the bottom. This negative 5 is going to create a 0 down here. But we need to ensure that we have the indeterminate form. So we plug in um, negative 5 into here, we get 4, 2 minus 2, 0. So we have that 0 over 0 indeterminate form. There should be something we can do, but we can see that there's nothing to factor out, right? So what are we going to do here? Well, recall that there's an identity which goes something like this. a plus b times a minus b equals a squared minus b squared. Just like that, right? So let's see if we can apply this somehow. You notice we have if we consider this to be a, then this could be b, so we have an a minus b, but let's multiply by an a plus b. All right, so let's multiply this entire thing by the square root of x plus 9 plus 2. But if we do it to the top, then we have to do it to the bottom. Square root of x plus 9 plus 2. And you'll notice that the top and the bottom just cancel out to give us 1. So we haven't actually changed the value of this at all. But now we can use that identity to change the top. This is just going to be the square root of x plus 9 whole squared minus 2 squared, which is 4, divided by x plus 5 times the square root of x plus 9 plus 2. Plus 2. Right? So now let's expand this out, right? This is just x plus 9 minus 4 divided by x plus 5. And we notice 9 minus 4, sorry, and then we have the x plus 9 plus 2 down here. And we notice that x plus 9 minus 4, this entire thing is just equal to x plus 5. So we got x plus 5 on the bottom, we got x plus 5 on the top. These are going to cancel out. And we're left with 1 over the square root of x plus 9 plus 2. Now that we've gotten rid of our x plus 5 on the bottom, because that was what was, creating the indeterminate form, we can just plug in x equals negative 5 here. So let's do that. We get 1 over negative 5 plus 9 is going to be 4. So then we're left with 2 plus 2, which is 1 over 4. And that's going to be our answer for this one. Okay, so we're done with the limits. I hope all of that made sense. If you have questions, drop them below in the comments. But now let's talk about derivatives, all right? Let's talk about the fundamental problem of like why we use derivatives. Let's say we have some function, just like this, right? Now, let's say we're trying to find the slope of the function at this point, specifically this point. Well, we already know how to find the slope in general, right? You just have 2 points, and we have that y1 minus y2 divided by x1 minus x2 or whatever. And that gives you the rise over the run, right? So we already know how to find it when we have 2 points, but how do we find it when we only have 1 point, right? Well, why don't we use 2 points, right? First, let's try it with 2 points. We have this point over here and this point over here. And let's just draw a line through them. Okay. Obviously, this isn't the slope of the basically what we're trying to find is the slope of the tangent line, right? The tangent is the line that touches this function at only 1 point. So it's kind of like the slope of this point on this function, if that makes sense, right? So we're trying to find this line, but we only have this 1 point on the function because we know that the function is like, f of x or something, but we're assuming that we know how the function is defined, right? So we only have this 1 point, but let's plug in 2 points on this function, right? And we draw a line like this, right? That's not that close to this line, but let's try again. Let's go a little bit closer. Okay, we're getting closer, Every time we draw a point that's closer to this function, and I know my lines aren't that good, but you can kind of get the idea, we get closer and closer to the actual function here. Okay, and this is kind of reminding me of those limits, right? We're getting closer and closer, but we're never really like, touching that point. So let's do that one more time, right? Let's say we have something like this, and we have 1 point right over here, and we have another point right over here, right? And we'll call the distance between this, we'll call it h, right? So now this is x, okay? Let's call this x coordinate right here x. And then since this distance right here is h, then this is x plus h, okay? And we know that this function is f of x. Okay, so now we have 2 points. Okay, we have 2 points, and let's just calculate the slope using these 2 points, right? So we have f of x plus h, right? Because this is the y value right here. That's the x value right here. So the y value is going to be f of x plus h, since we're plugging that in, minus f of x, because that's the y value of this point right over here, if we're calling this x, divided by our first, we're just going to have x plus h here. That's our x1 minus x. We notice the x's cancel out. So we're just left with f of x plus h minus f of x divided by h. Okay, but what did we say? We're trying to find it just at this point, right? Just at this point. So we need our h to be as small as possible to be as accurate as possible. In other words, h tends to 0. So this is what we call a derivative. And using this function, we can plug in values of a function to get the derivative. To get the derivative or the slope of the function at that one point, the slope of the tangent line at that one point. Okay, and I have another video on this, so I think that has a couple more examples. You can go more in depth there if you want. But now we're just going to talk about the power rule, right? Now that we have so say we have x squared here, right? Let's say this is the function y equals x squared. And we know that let's figure out like the slope at a couple points, right? Remember our formula is f of x plus h minus f of x divided by h, right? Okay, limit h tends to 0. Okay, so first we're just going to plug in x squared for f of x, right? So now we have x plus h whole squared minus x squared divided by h. Okay, and we're going to continue simplifying this. We're going to continue simplifying this. We get x squared plus 2xh plus h squared minus x squared divided by h. And then these cancel, and then the h is going to cancel up here. And we're left with 2x plus h. But the thing is, we already know that um, h is tending to 0, right? Because this is limit h tends to 0 if we're trying to find the derivative. So now we're just left with 2x because this h tends to 0 and it's gone. So now we're just left with 2x. What does that mean? If we find an x value at any point and we plug it in, the slope of this function, x squared, is going to be equal to 2x at any point. And this is what we call finding the derivative of a function. All right? And you'll notice something funny happened here. X squared, the derivative of that is 2x. And we write derivatives like this. X squared d by dx equals 2x. Okay? So we notice we just kind of brought our 2 down like this, right? And we just brought it to the front. Let's try to figure out what the derivative of x cubed is. Now you can do that on your own, but I'm just going to tell you right now, it's 3x squared. All right? So we got 3x squared. Let's see what the derivative of x to the fourth is. It's going to be equal to 4x cubed. Okay, so we're starting to see the pattern now. Basically, the derivative, this is called the power rule. The derivative of x to the n equals n times x to the power of n minus 1. This is going to be your power rule, and you're going to use this to figure out like some derivatives. All right? Okay. And you're going to use this a lot, so make sure you keep that in mind. Okay, now let's talk about the chain rule. What if instead we had something like x plus 6 to the power of 2, right? We already know that the x squared, or let's say we had 2x plus 6 to the power of 2. We already know that x squared, the derivative of that, is 2x. But how can we figure this out when we have like a 2x plus 6 in here? Well, the chain rule basically says that f d by dx of f of g of x is going to be equal to f prime of g of x times g prime of x. Now that looks really complicated up front, but I think you come to see that it's not that complicated in practice. Right? Okay. So let's see here. F prime of g of x. Okay, so our f prime is going to be 2x, but instead of 2x, we're going to put in g of x. And our g of x is the inside thing right here. Okay? So that's going to be 2 times 2x plus 6, because the inside thing there is our g of x. All right? And then we have our g prime of x over here. So now we can figure out the derivative of this. the derivative of a constant is always just going to be equal to 0. So the 6 goes away. And the derivative of x times anything, so if we have like c of x, the derivative is just going to be c, right? Uh, so we're just left with uh, so we're just left with c here, which in this case is 2. We have 2 over here. So this is going to be the derivative of that function using the chain rule, and using the chain rule in addition to the power rule. Okay, so now that we have the derivative function, we can try finding the tangent line. Whenever they ask you to find a tangent line, they're going to give you a point to find as well. All right, so the first step is let's just do this with x squared again here, right? So let's come over here. Let's just do this with x squared again, right? And they ask you to find the tangent line at x equals 1. They ask you to find this tangent line right here. So first step, we're going to have to find the derivative, because when we're trying to find a line, we either need 2 points or we need the slope and 1 point, okay? So first we have x equals 1 over here. First, let's find the derivative. We already know that the derivative of x is 2x according to the power rule. All right. Uh, and then we can just plug in x equals 1 here. And we know that the slope at this point is immediately just 2. All right, now we have y equals mx plus b, right? Slope-intercept form. We know we know the slope is 2, 2x plus b. Now we just need a point. We're trying to find it where x equals 1, right? So we'll just plug in, we'll just see what the value of x squared is when x equals 1. And we know that 1 squared is just equal to 1. So now we know that x equals 1, and that we know that x equals 1, and that y equals 1 as well. So we have 1 equals 2 times 1 plus b, and then this is going to be equal to 1, 2 comes to this side, -1, that means -1 equals b. So we have y equals 2x minus 1, just like that. All right? And that's basically the function of this line right over here. Okay, so that's basically all I have for you. Um, the last thing is basically just these uh, important identities. All right, so these are all things you want to keep in mind. The limit of x tends to 0 if sine x over x is equal to 1. Limit of x tends to 0 if 1 minus cosine x over x is equal to 0. And the limit of tan x over x is equal to 1. X tends to 0. Now, limit of x tends to ac equals c. We see there's no x in here, so the value is going to be the same at any value of x. It's just going to be c. Limit x of x tends to a is just going to be equal to a, because x is just going to go to that value. Makes sense. And then all that these ones are saying is that if you have like compound functions or something like that, the limit you can just put it inside, right? And you can evaluate the limit separately, and then that's going to be equal to the limit of the whole thing. All right. We have limit 1 plus x to the power of 1 over x equals e, and 1 plus 1 over x to the power of x also equals e. This is for x tends to 0, this is for x tends to infinity, and these are basically like the exact same thing, just in like different forms. And then finally, limit x tends to infinity for 1 over x to the power of n equals 0 for anything that where n is greater than 0, which makes sense. It's pretty intuitive. We did it with 1 over x earlier. Limit x tends to infinity of ln x divided by x is going to be equal to 0, which is slightly less intuitive, but also makes sense because ln x increases really slowly and x increases a lot faster. In general, if you see something increasing like pretty slowly on the top while something on the bottom increases a lot faster, then when it goes to infinity, it's going to tend to 0. And then x tends to infinity, x to the power of r over e to the x is going to be equal to 0. And this is basically because e to the power of x is exponential, whereas this is not exponential. This is just x to the power of something, right? So since exponential increases a lot faster than this, you're going to see this is equal to 0. And yeah, that's it. Hope you enjoyed. Leave any questions in the comments.